And following our agenda, now we have a segment that is about the EPI common platform. This will be covered, this will be led by Sylvie. And there will be, I think, contributions by Denis and perhaps Etienne, right? Thank you for taking the initiative to fill us in on this important part. Yeah. Okay. You're right.
This one.
Yes, yes.
Okay, thanks. So thanks, Manolis. I will introduce the EPI Common Platform that is part of the EPI project. I am Sylvie Lesman, technical leader for EPI, but I am working in Eviden after 20 years in ASIC development and simulation. I am since 15 years in server development at Atos Eviden as an architect. And here we wanted to introduce the EPI common platform in this co-design workshop because it's part also of what we call co-design here. So we all know that we want to create an ecosystem with this project, and from the processor and accelerators technologies to the application and software ecosystem. And so as we implement both the general purpose processor and the accelerators, we propose to define what we call a common platform to design both type of component and the associated programming environment that target both the stream for general purpose processor, but also the streams for accelerators. That's why we call that a common platform. And we focus on two areas, the hardware part, the hardware common platform. And for that, the idea is to design decoupled system with closely coupled performance. So what do we need to do to achieve that? And the software common platform is more to define the software stack that we have to optimize for hybrid computing. So I will speak a little about the software common platform, replacing Romain Dolbeau from Cypher, who mainly worked on this subject and who attends remotely. So why do we need a software common platform? Mainly, in fact, we want to provide the building blocks that are necessary to make sure that our software supports efficiently both general purpose processor, accelerators, either each one separately or together. And it's very important to have all the software ecosystem to do that. So I will not come back to already speak about the fact that ARMv8 and RISC-V has been confirmed as interesting and mature technology for ARM. But what is important is that EPI has worked on all the levels of the software stack. And so we have contributed to the maturity of this environment. And so, as usual, the software stack is the software libraries, programming model, internode, intranode, the compilers, operating system. And we really want to propose to any user user code what he needs to have in order to be sure he will support the new hardware. And what is important, without rewriting a lot of things in the code. And so how did we work for that? In fact, the problem was to select which standard we will say are important to support. And so we did some survey around all the partners in the HPC area to check which tools they are using, tools, framework, libraries, and try to understand what is used, what is not, compared to what could be needed. And so we identified some critical areas that needed to be well supported, and all of that, this survey and the result of the survey is available in deliverable. We will not go through all that here, but you see in the figure here an example of the type of result we got from the partners. And so what are the recommendations? First, again, we contributed a lot to the software stack. So Linux kernel, LLVM compiler, libraries, tools. And at the end, the recommendations that we can do are rather simple. What is important for the users to well support this type of hardware is to favor open standards for the programming models, internode, for internode MPI, for intranode OpenMP, inter-device offloading, more OpenCL or CKL or OpenMP target. So it's such type of tools that are really mandatory to be well supported. And for hardware developers, it's important to support at least the standard language, so C, C++, Fortran, and also one standard offloading model. And today, maybe OpenCL, CKL, or OpenMP target. And of course, avoid proprietary solution whenever possible, even if you know it's not always feasible. So the survey really shows that does not show that there are something important that we had not in mind. It confirms, in fact, what is important for that. And now I will let Denis for the hardware platform.
Thank you, Sylvie. Okay, so on the hardware side, there is, like the software side, a dedicated work package for EPI. I have been involved at the very beginning of the project in the definition of the hardware common platform, and now it's Anthony Philippe, who is responsible of this platform and who prepared these slides. So on the hardware side, what was our initial ideas and objectives? So at the very beginning of the project, the consortiums understand that the interest of multi-dice chiplet approach, as we said this morning, for scalability, heterogeneous architecture, yield improvement, and cost optimization. And we haven't started some die-to-die studies for advanced packaging during the very beginning of HGA1 based on HBM2E5. We even made some technical presentation about that. Then we worked as well in collaboration with IP providers. Because for this common platform, we need, you may understand, the interfaces. So we've studied the dedicated network on chip interface and the related die-to-die data link layer and PHY. And we are pushing for our use cases and requirement support. So at the beginning, during the project, we've defined what are our use cases in terms of common platform and hardware common platform. So there was, we identified 3 use cases: rear to rear in SMP mode, rear to specific accelerator for compute specialization, and open platform. I will provide you with a little bit more detail just after. So, first of all, starting from the early stages of this multi-die system, our very first intent was to define, promote, and push or let's say on a European die-to-die communication standard. But you've seen as well this morning, the landscape is moving very fast in this area. And there was a creation of Open Compute Project ODSA, a UCIe consortium that bring us to rather take part of the global standardization process instead of trying to promote and to develop our own protocol, which will be unique and perhaps not really used. Okay, so just to have an illustration of this moving landscape of die-to-die interface and hardware common platform. So at the very beginning, there was the ultra short twitch, just a very quick laser pointer. Okay, so let's start. Before EPI, there was existing interfaces with based on SerDes, and then major players had their own releases of interface. For example, Intel with IAB or NVIDIA with several releases of NVLink, release 3.0, then 4.0, 5.0. Same for AMD with several releases and integration of accelerators. So several releases of the Infinity Fabric. At the same time, some open initiative were created, like ODSA, with then several releases of bunch of wire. And the last one, but perhaps now the most mature one, is the UCIe consortium with release 1.1, 2.0, and next to come next year, the 3.0. So that's quite a moving area in terms of a moving ecosystem in terms of die-to-die interfaces. So on our side, we've tried to follow everything. We've started with the first die-to-die studies, as I said, with perhaps our own protocol. Then progressively we join, let's say, existing consortia like Cypher, who joined CXL consortium in the middle of XGA1. And then we worked on existing standard by comparing them. And at the end of the project, we are focusing on UCIe development. And we are trying, and we have made the exercise to map the EPI use cases on UCIe. Just to, okay, we talked about that this morning. UCIe is both a layered approach for hardware protocols from the IOs, so at the file layer, up to the protocol layer with the support of PCI Express, CXL, and also some streaming interface with, for example, ARM CHI chip-to-chip for as a streaming protocol. And it's UCIe is as well defined as a stack, software stack with basic control flows and some important features that for in-field deployment like RAS, security, interoperability, and so on. Okay, so as I said, we have defined 3 use cases, 3 usage, let's say, on for EPI. The first one is symmetrical multiprocessor, this one, to enable multi-assembly in a single package for scalable solution. So this usage or use case is supported by UCIe IP because we can use from UCIe protocol the native streaming interface. And what is interesting with the UCIe is that we can use an existing IP from an IP provider. The second use case is the accelerator mode to enable the integration of an application-specific accelerator to REA chip. Then UCIe interface, which implements both PCI Express and CXL, is and also preferably for us, for the case of REA, the ARM chip-to-chip protocol is also a good match for this usage. And finally, the third scenario, the third usage or use case is the open platform to address a completely new market of a system with assembled with die from different vendors and technologies. And once again, this use case is fully aligned with the UCIe main objectives and roadmap. So what we can see that for the free usage or use case we've defined for our hardware common platform, all of those three use cases are supported by UCIe. So the lesson learned on hardware common platform are the following. We have identified the three important die-to-die use case for the EPI hardware common platform: SMP mode, accelerator mode, and open platform. So based on a hinted comparison of the different die-to-die available standard, so the EPI project recommend the usage of the UCIe standard. For which reason? For performances, maturity, availability through different technologies, because chiplet could be defined in different technologies, but also for market penetration and strength of its consortium. So whatever our recommendation, which is to recommend UCIe, the final decision about IP selection remains in the hand of the industrial partners building their own compute SoC. Depending on other constraints than technical one that are industrial constraints, volume forecast, potential commercial agreement, or sometimes very simply some business opportunities. So we are open for discussion, questions.
The idea here it was also not only to have questions, but try to have a more open discussion on the common platform with the
Of course.
people participating.
Let's thank our contributors for their nice summary. Who wants to say a few words in response to that? Nico?
Hello, thank you for your presentation. I'd like to ask if you have identified any significant software gaps in the ecosystem. I noticed during your presentation that the GNU is a large portion of what's going on. And it's also something we are talking about within RISC-V International and other bodies, like what parts of the software stack should we cover?
For that, perhaps Romain, are you online?
Yes, but I didn't quite catch the question. Can you repeat the question?
Yes, so I was wondering if you found any significant software gaps in the software ecosystem.
It all depends if you're talking ARM or acceleration, right? On the ARM side, there were significant gaps and lack of maturity when we started as year one a long time ago, the first part of the EPI project. But between the work we have done, the work that other projects have done, on more importantly, the work the entire community has done with the support of the ARM architectures, not just on mobile on SBC, but as on the server side with the offerings from Amazon and Oracle and Ampere and others. there is no longer any major missing pieces. You can always do better, obviously. The software situation on ARM isn't perfect, but there is no major issues left. What we are now doing mostly in various projects is performance improvements and things like that. And in other projects, we also have collaboration on more advanced tools that are specific to area like HPC, such as more advanced profilers and things like that. So that's the first half of the answer. The second half would be on accelerators. And there, the conclusion of the study that we've mentioned is that ultimately, it's sort of in the responsibility of the hardware developers to supply the adequate part of the tool chain that are needed. So compiler have offloading infrastructures. We have things like the SQL or OpenCL/SQL infrastructure. We have things like ONNX, if you're interested in AI and things like that. And as long as the user are targeting this clear target of using standard languages, standard tools, standard frameworks, then it's only the responsibility of the hardware developer to supply the specific parts that are needed, such as code generation, a runtime that can talk to on drivers that can code specifically to their own accelerator or piece of hardware, etc. Obviously, that part is much more complex to define, because even if we are working on it in SGI2 for the various accelerators, it's much more difficult to finish, and unless you already have access to the hardware and you can actually try, because simulation is great, but ultimately when it comes to fine-tuning and stabilizing, you need to run tons of codes, tons of workloads to make sure the software infrastructure is fully stable on top of the hardware. So I would say on the ARM side, we are essentially, if not at parity with legacy architecture like Intel, close to it. For accelerators, it still needs some refining in terms of supplying the tools needed for the users, and provide a compelling reason for people to start migrating away from, let's use the word CUDA, to more standard options that can use a wider range of hardware, including the hardware developed in the API.
And in terms of RISC-V, do you have any idea about the gap there?
That's whatever I'm going to answer, I'm sure that history will prove me wrong, right? It's moving faster usually than we expect, I would say. There is quite a number of boards by now that are available that offer a wide range of features. And today, I would say the software stack on RISC-V is, at least if we take the broad server kind of market, not anywhere near as ready as ARM. If we look at embedded, it's much easier, because usually the software needed is much more restricted in terms of scope, and there is much less concern about field upgradability and things like that. So having very branded bootloader, let's call it that, because that's what they are, is not that much of an issue. Having proprietary, or at least vendor-specific kernels and bootloader and things like that is not as much of a problem, but it's moving very fast. My belief is that the availability of boards at a reasonable price point implementing RVA23 will be a very important milestone. Ubuntu has made an announcement about only supporting RVA23. Other distribution were very interested when we discussed in a panel, that was discussed in a panel during the European Summit. I think that will make things move much faster, because it will be a much cleaner, much more reasonable baseline on when hardware vendors start to cleaning up the mess of the boot systems, which is an issue that ARM has had on their embedded side and still has in some aspect. It will help things move much faster. But I'm not going to risk, giving you a date, because whichever date on how big a range I pick, I'm going to be wrong unless I say, between now and on the end of time, it's going to be server ready.
Thank you.
But I'm not going to risk being any narrower than that.
Any further questions or comments? Well, for the RISC-V side, I wanted to add that there is this association by industry partners RISE that have been maintaining what is called the landscape of software for RISC-V. It's getting better, started in 23, I think, but they had identified gaps in almost all layers of the stack. For ARM, as was said earlier, there is a lot of progress. We had the historical perspective given in the morning session by Jean-Pierre Panziera, how long it took and what level of investment it took to create a reasonably complete and robust software stack. So let's keep that in mind. It's kind of a sobering thought, but we know that it can be done. Now, on the hardware side, we had the keynote in the morning by Denis. One point that he highlighted was that it's not just to be compatible on the physical level, but also the protocol level. And I wanted to kind of challenge you here in a nice manner, probably. Are we there yet? UCIe is making strides, but is the protocol aspect, in your view, being handled properly? Are we going to have indeed chiplets that can be reasonably mixed and matched in a time frame of, let's say, 2 or 3 years from now? I'll put a time frame there as well. That would be, I think, relevant to the common platform, but which I think stands on its own as a concept, but on the particulars that we have at hand for a possible realization, perhaps chiplets are part of the answer, right?
Just you mentioned that the at system level the protocol is important and everything exists. I mean, UCIe is compatible with CXL, compatible with PCIe, and and also with any streaming protocol. So if you design the 2 chips like the SMP use case, then you can have a fully interoperable system because you know the protocol on both sides. Now the issue is when you have the use case with an accelerator and a GPP, then you can have some kind of business agreement, let's say, to say, okay, I take your accelerator only if you have this protocol. When you have a completely open platform, then you have to be compatible with any protocols at a higher level. That starts to be very, very complicated. So that's okay. That's the issue of such.
Actually, I was hinting at that a common platform set of standards or initiatives sets the basis, but realistically, at this point, we have seen that either you need a major vendor or a coalition of major vendors to actually lead to a physical product. But nevertheless, I think the common platform was an early contribution of the EPI project, and it was, I think, at the time, I think it provided a comprehensive view of what needs to be addressed, and that I think carries value on its own. And I'm happy to have this topic being discussed several years later and with some evidence of progress, I think. Other comments or questions to our contributors?
Hi, thanks for this great information here. Of course, I've seen lots of this in the past. So my question or my worry more is, I mean, is UCIe or an equivalent protocol suitable for chiplets of, let's say low-cost chiplets of, let's say 22 nanometer technology, 16? Would it cost a lot of area? Would it cost, how do you see this thing? Is it?
Yes, this is another story. So UCIe for which market? Obviously, UCIe has been designed and developed, let's say, specified mainly for intensive computing. So for HPC, that's fine. You're right that for other markets, so let's go to, for example, automotive market. UCIe is also a good candidate for the automotive market where you can have lots of intensive computing. Now, when you are going to, let's say, IoT or microcontroller market, so you will not use UCIe. If you want to connect, for example, an accelerator to a microcontroller, use a quad SPI, not a UCIe.
Yeah, I had similar thoughts, and now for the, how to make these interfaces. I understand that you have options to have it 16 pins, 32 pins, 64 pins, some number of pins where you use the UCIe. So do you think that there can be something more generic than this, or like I don't know, lanes that you can negotiate or negotiate between the chiplets, or things like that? Or is it like maybe it's included in the protocol and I haven't seen the details, but could it be something that is, let's say, backwards compatible and can scale depending on the other end? Or
Yeah, you can scale it through the number of lanes, or I don't know exactly the exact name, but the equivalent of lanes or module. You can scale it with different frequencies. So you have a kind of scalability within this protocol, but it is always a compromise between cost, let's say number of pitch and number of pins, versus latency. Because if you want to multiplex everything in a single lane for cost reason, then you had latency. You need forward error correction, which is not good for SMP use case, because you need you don't want to have. So that's a matter of compromise. Difficult to say yes or no, or black and white. Just compromise.
would you like to?
Yes. So I think one question we have now is perhaps if we project in the future. We talked, for instance, with Matteo this morning about Zetascale computing. So if we project, let's say, 10 years time in the future, what could be the right solution to ensure a smooth and an efficient collaboration between the GPP, which may be probably more rare in the proportion in the global mix of supercomputers, and the accelerator, which may be more adapted to various application use cases, and so with part of customization. So I would like maybe you or maybe in the room to have some insight of how can we imagine the future of this problem which we are facing in the project, but which is not certainly not restricted to the project. It's quite a general question.
That's a huge question. That my personal, let's say, personal feeling that you will always have a need of a general purpose processor for connecting everything together, for parallelism. Now, how do you connect a kind of multi specialized accelerator? So you will need a kind of interconnect for that, what we call a scale-up one. That has to be defined. For on the hardware side, that's not so. That's quite complicated to have heterogeneity and also scalability. So that we have to merge both, and we need interconnect. Which one? UCIe is not 2D mesh. It's it's a connection between dies. So we have to go from let's say just die to die to a complete new interconnect. That's not so easy.
And what we could say also is that if we want to have some hardware that is flexible with a lot of types of accelerators, it make me think to the disaggregation that we see now, where we say we have the memory on the one side, the IOs, and so on, and so several type of accelerators. It was not really, it's not really feasible today, but optics probably may change the way to do that, because we might have some connection that are efficient and with a longer path. And so all this disaggregation will have to be thought with optics and taking into account also this part. So it's a little a balance between saying we will integrate much more things with different chiplets on a package. And on the other side, we say we will have a maximum flexibility and programmability. And so we have to find a good balance between the two, because they are a little antinomic at some points.
We can optimize compute thanks to specialized accelerator, but we don't have to forget memory, which is a major point in terms of power consumption. So if we lose we have to access to very long access to memory, we lose everything. And interconnect, because if we have plenty of accelerators, we have plenty of interconnect. So that's the 2 points that has to be solved if we want, let's say, a plurality of accelerators.
Okay, and if we take this aggregation view, as we were discussing earlier during Mateos's presentation, I think there is a lot of pressure on the system software to actually realize that. And I think the common platform as introduced by EPI and does not block this view, but it's not a disaggregated system view. It's an integrated stack. It's an integrated system with many tunables and lots of, shall we say, robust interfaces, but it's not directly a disaggregated system, which is for thought on its own. Any further reaction or comment about the common view? Perhaps from the people on remote. We heard some contribution by Roman earlier. Roman, anything else that you would like to fill in, particularly on the software aspects?
No, I think
Okay.
that's okay. Unless there is further question, obviously.
That's fine. So